All right, welcome everyone. I'm glad you're able to participate today in this webinar entitled Diaphragm Deflection Design. It's taken from the 2008 Special Design Provisions for Wind and Seismic. As Dawn mentioned, this is a program that's accredited by AIA. And so if you need those credits or a certificate of completion for this program, you'll receive that at some point after today's presentation. Also a reminder that these are copyrighted materials, and we won't spend any more time on that than necessary. We'll get right to the substance of the presentation. Today's learning objectives are to be able to calculate wood frame diaphragm deflection using the 2008 wind and seismic provisions. You'll see abbreviated in the code as SDPWS. I typically refer to it as the wind and seismic standard, and so you may hear me using both terms throughout the presentation. We also will compare the differences between the 3-term and the 4-term deflection equation in the 2008 edition, and analyze individual components of deflection equations to determine their magnitude of impact on total deflection. And then hopefully you'll be able to utilize this deflection calculation in future design work as a model for your own calculations. A related webinar took place back in October where we covered provisions of the 2005 and the 2008 Special Design Provisions for Wind and Seismic. It is both in ASD and LRFD format. So we'll make some assumptions today in the presentation that you're already familiar with some of the provisions that are in the 2008 and the 2005 version. If I use some terminology or some assumptions that you're maybe not familiar with, you're able to go back to the woodworks.org website and stream that presentation free of charge. So you can take a look at that on your own at some point. So a real simple outline for today. We'll just talk quickly about the code acceptance of the 2008 Wind and Seismic Standard in the IBC. We'll provide an overview of the diaphragm deflection equation as it's presented in that standard, and then we'll work through an example. And I'm hoping to leave plenty of time at the end for questions along the way as well. So as I mentioned, the wind and seismic provisions are referenced in the IBC, the International Building Code. And in the 2009 IBC, the reference to the standard is actually mandatory. In the 2006 IBC, the reference to the 2005 wind and seismic provisions was optional. And what you're seeing happen there is that these wind and seismic provisions are being taken from the code and incorporated into an ANSI consensus standard. While the code adoption process that ICC uses has been around for many, many years, we feel like the ANSI consensus process provides a lot more rigorous approach to developing standards. And so instead of a couple of minutes of testimony at the microphone at the hearings, we're actually able to deliberate for hours at a time some issues as we develop these standards. And so that's why you're seeing that transition from provisions that are transcribed in the code to provisions that are incorporated into consensus standards and then referenced by the code. So we'll jump right into Chapter 4 of the Wind and Seismic Standard, which provides the three-term diaphragm deflection equation that is an algebraic simplification of the 4-term equation that you see in the International Building Code. And we'll talk more specifically about that simplification and how we got there. But the same tables that specify nominal unit shear capacities also contain the values of apparent shear stiffness, or G sub A, that you see there in the middle term. And we've reformatted this to simplify the deflection calculations and to extend it to a variety of other sheathing materials and unblocked wood structural panel diaphragms. As I mentioned, it is an algebraic simplification of the four-term equation, which you see here. And this four-term equation is actually not only incorporated in the IBC, but it's incorporated in the commentary of the Wind and Seismic Standard, and provides some more definition of the terms that are used in the equation. The first term, we'll look at each of these in a little more detail, but the first term handles chord deformation, excluding slip. The middle two terms handle panel deformation and nail slip, and then the final term handles chord spliced slip. The Wind and Seismic Standard provides you the option to use this four-term equation if you so choose. So the first term of the equation is for bending, chord, deformation, excluding slip. And you see the term V, there's the induced unit shear. L represents the dimension perpendicular to the direction of the applied load. E is the modulus of elasticity of the diaphragm chords. A, the area of those chords. And then width, W is the width of the diaphragm in the direction of load. The third term of the equation, and I'm jumping around here on purpose because we'll look at those two middle terms together, but the third term handles chord splice slip, and X defines the distance from the chord splice to the nearest support. For example, a shear wall aligned parallel to the loaded direction of the diaphragm would typically be considered a support. Delta sub C is the diaphragm chord splice slip at that induced unit shear, and then again W, the width of the diaphragm. And then we have those two middle terms of the four-term equation, which has been again simplified for the three-term equation. In the left-hand four-term equation, the G sub V, T sub V represents the shear stiffness. G sub A is the apparent diaphragm shear stiffness, and E sub N is the nail slip. We get that simplification, and this equation for G sub A is actually defined in the commentary of the Wind and Seismic Standard, but this G sub A term is actually tabulated in the panel shear stiffness tables, and is used to calculate the component of deflection due to shear deformation. And it replaces the need for some of those intermediate calculations that separately account for nail slip and panel shear stiffness. Now, one thing I do want to point out here, and it's highlighted in red, and we've had questions about this before, but because this is a simplification where we actually have to tabulate these G sub A values, we do make an assumption that that G sub A is based on 1.4 times the ASD unit shear capacity versus the induced unit shear. So that's a distinction that you need to be aware of. Again, you're still permitted to use the four-term equation, But I think you'll see when we look at the results here in our description and then later in our example that making this assumption about unit shear capacity versus induced unit shear does not change your results dramatically. In fact, it matches up quite well with the test data, and we'll take a look at that as well. So if you're using the four-term equation, those values of G sub V, E sub V, shear stiffness, are also included in the commentary to the wind and seismic standard. Anytime you see a table with the title or the number for the table starting with C, you know that that's part of the commentary. So this is commentary table C4.2.2a, which tabulates shear stiffness values for wood structural panels. We also tabulate shear stiffness values for other materials like plywood siding, particle board, fiberboard, gypsum, and lumber. Again, looking at how we calculate G sub A, the equation that we looked at earlier, we use the fastener slip, E sub N, to calculate that G sub A value. And another question that has come up, actually as recent as last week, was what nail spacing do you use to calculate the fastener slip E sub N if you're using the calculation approach or the four-term equation? And the answer is to use the interior panel edge nail spacing. And I've highlighted it here again in this table from one of the tables up front in the wind and seismic standard. And again, as we look at the test data, which is coming up here in a little bit, to compare the two approaches, you'll see that this is a reasonable approach. Just so you know, this was a fairly hotly debated topic in the standards committee. Not all engineers agree on this approach, but this was the approach that prevailed. And as always, as engineers, as structural engineers, you have the ability to add engineering judgment to your designs. So just be aware of the assumptions that we make in the tables. We try and spell that out very clearly in the commentary, but there's still room per the code for engineering judgment. And again, for that derivation of G sub A, we try and provide clear examples. You see the equation here that we looked at earlier that is used to calculate G sub A. So we worked through an example here in the commentary that shows you how we came up with the value in table 4.2a of the wind and seismic standard for a certain sheathing grade, sheathing layup, nail size, panel thickness. And as you work through this example, you'll come up with this value of G sub A, 15 kips per inch, that is tabulated in the wind and seismic standard. So again, we're making it as clear as possible what assumptions we're making to come up with these values. So how does that match up with test data? And as I mentioned earlier, we use or we calculate deflections at 1.4 times the induced or the shear capacity, and that very closely matches up with the test data for both blocked and unblocked wood structural panels. As you can see here, for different cases of blocked and unblocked, this is the actual measured deflection in the tests. These two around 1/4 of an inch These two here, the block obviously less than 1/4 of an inch. But then we come over here to the calculated deflection, again using the G sub A simplified approach, and you see that we're within pretty good range of those actual deflection calculations. Graphically, it looks like this. That 4-term equation is a nonlinear equation represented by this dashed line. The 3-term equation is a linear equation represented by the solid line. As you can see at this point here, at 1.4 times the ASD capacity, which is what's required per the ASCE 7 standard, the values you get will be identical. And out here in this range where you will see some variance, it's as little as 0.045 inches as the maximum difference between the 3-term and the 4-term equation. Again, that's 0.045 inches. And so we feel like that small a difference is not necessarily significant in design, but you need to be aware that that there are those differences. But at 1.4 times the ASD shear value, you're going to get identical results. So that's the background for the 3-term and the 4-term equation. We're going to jump now to the example that's spelled out in the commentary to the wind and seismic standard. Again, trying to cover some of the assumptions that we make. So again, in the commentary, you know that you're in the commentary when the examples are preceded with the letter C. So this is example C4.2.2-3. We're going to calculate the midspan diaphragm deflection for a diaphragm with a length of 48 feet, a width of 24 feet, splices at 16 feet on center in the diaphragm chords. If you look here in this note, you're going to see this is a case 1 block diaphragm, 7/16 inch OSB sheathing, 8 penny common nails at 6 inches on center at all panel edges. The allowable stress design load is 255 pounds per linear foot. The shear diagram looks like this, with the shear at those joints, at those chord splices, 65,280 foot-pounds. The maximum shear here in the middle of the diaphragm, 73,440 foot-pounds. So that's important because when we do the analysis later, we're going to be analyzing those chords at the splices. But if you are not sure where those splices are going to turn out in construction, you may want to use that maximum moment for your calculations. So first thing we're probably going to want to figure out then, over here on the right, is what are the number of nails required to calculate or to resist the chord forces. So again, at those splices, which are at 16 feet on center, we're going to use the moment at that location, 65,280 foot-pounds, divided by the width of the diaphragm to come up with the required tensile force or compression force. And using a capacity from the NDS, the National Design Specification, for a 16 penny common nail, we see that we need 12 nails. Now, again, if we had used a maximum moment here in the middle, I think we'll see that calculation a little bit later on, then we'll come up with a requirement for more nails than that. Oh, I see I had blown up the diagram here. Sorry, I covered all that in the previous slide, but that maybe gives you a little bit clearer view of the dimensions of the diaphragm and cord splice locations, maximum shear, and moment for those. So then we're going to go to table 4.2a of the Wind and Seismic Standard, and you see that for the nailing, the nail size, the common nail size, the panel thickness, we had 2x materials at the boundaries. We come up with a shear of 510 PLF, and per the footnotes of the table and the standard itself, you divide that nominal capacity. This is a nominal tabulated shear capacity. You divide that by 2, but then your G sub A doesn't require any further adjustment. That G sub A apparent shear stiffness is 14 kips per inch. Okay. Another point that I'll come back to here as far as calculating the number of required nails in the cord splice is that we make an assumption here that the upper plate is designed as the continuous cord, and the lower plates would act as splice plates. Again, that's engineering judgment. So we're going to assume the cross section of this diaphragm cord is the cross section of 1 2x6, even though there are 2. But if you think about that for a moment, right at the cord splice, which is here, right above the red dot, what is your true cross-section of that diaphragm cord? Because you've obviously got a break in the cores here, so your cross-section on this top plate really is going to be 1 2x6. So we'll look at that in a little more detail, but again, that's another assumption that we're making. I'm sorry, I'm showing that splice location incorrectly. The splices are actually here. Joint A and joint B. Sorry about that, but you are going to have a similar joint here underneath in the bottom plate, or the bottom top plate. But in any case, wherever you are at those splice locations, your cross section really is going to be for 1 cord member. Now we know it's probably a little more than that, but that's, again, an assumption we're making for this example problem. So we talked about this earlier, calculating the number of nails required in the cord splice. I probably jumped the gun a little bit, but you can see it spelled out a little more clearly here. A little bit bigger text to make it clear, but we're using the maximum moment at the joint splice locations divided by the width to come up with the number of nails. And I think I mentioned earlier, if you were to calculate the capacity or the number of nails at this maximum moment of 73,000 plus foot-pounds, you'd actually come up with 14 nails required. So you have to decide where your splice locations are going to be to perform that calculation. So now we're going to calculate the mid-span deflection once we have the number of nails. And again, we're going to pull out that 3-term equation that we looked at earlier. We're going to use that since that's what's shown in the standard. Again, we went through all the allowances for using the 4-term equation, so that's still there. But for this particular example, we're going to use the 3-term equation. So the first term is deflection due to bending and cord deformation. So we'll look at each of these terms separately. Again, ASE7 requires that seismic story drift be determined using the strength level design load. So we're at 1.4 times the induced unit shear. Then we're looking at the effect of chord splice slip on chord deformation. Or I'm sorry, we're excluding chord splice slip in this particular example. We're just looking specifically now at bending and chord deformation. We're going to look at the chord splice slip in equation term 3. So right here we're just looking at the effect of bending and chord deformation, bending of the chord itself. And again, the assumption we're making is that we're using one top plate to resist that induced axial force. The second is a slice plate. That's engineering judgment. But if you look here, even if we were to double this cross-sectional area here to 16.5, or no, it would be, yeah, to 16.5, you're going to change your deflection for this part of the equation to 0.04 inches rather than 0.08 inches rounded. So again, not a significant difference depending on what assumption you make for your chord cross-sectional area there. Now we'll look at the deflection due to the shear, the panel shear, and nail slip. That's the middle term of the equation. We spent a lot of time already looking at that. Again, 1.4 times the induced unit shear. Length of the diaphragm of 48 feet. So we're just plugging numbers here. That G sub A value that we pulled from the table, 14 kips per inch. And you see that this part of the equation is going to end up being the most significant of the three parts, 0.306 inches versus 0.07, I think, for the other two components. So that's the middle term of the equation. Then we're going to look at the third term of the equation. It has a couple of different parts here. In earlier versions of the standard, even in this version, finding these values was a bit tricky. We'd get calls from folks wondering where some of these values came from for this part of the equation for chord splice slip. X is pretty easy, as we defined earlier. That's the distance from the joint to the nearest support. And in this case, each joint is 16 feet from the nearest shear wall at the ends of the diaphragm. But then we get to this term, which is the joint deformation due to chord splice slip. And that was often a question that we get to our help desk: where do we get those values? So you see there's an equation here that's incorporated into the example problem. We're looking at the 2 times the tensile or compressive force divided by this term gamma, which we'll define here in a second, and the number of nails. Well, that term gamma then is the actual load slip modulus for a particular type of fastener. And for this particular fastener, which is a 16-penny nail, we would turn to the NDS, Chapter 10, Section 10.3.6. It's actually part of the group action factor equation, where we define this load slip modulus for nails. In this particular case, it's 180,000 times the diameter raised to the 1.5 power. So that gives us a nail slip in pounds per inch per nail of 11,737 pounds per inch per nail. So you plug that into the equation. You come up with a tensile force, again, based on 1.4 times that induced unit shear. And I believe this next slide then will give us the results for that particular portion of the equation of 0.05 inches. And again, we use a constant of 2 in the numerator to account for slip in nail splices on each side of the joint. Then we're going to go back to the original equation. Since we've calculated all those values, slip at each one of those locations. We're going to add those up and divide by the width of the diaphragm to come up with the tension cord slip calculation. Again, that's just for the tension cord. We're going to make an assumption with the compression cord that the compression cord butt joints have a gap that exceeds the splice slip, so that the tension cord slip will also be used for the compression cord on the other side of the diaphragm. So that gives us a total deflection due to cord slip of 0.07 inches. And then we jump back to our original equation. Again, the first part of the equation that we were looking at due to the bending cord deformation, that's going to be around 0.08 inches. The middle term due to panel deformation and panel nail slip, and then the final term that we just calculated due to the cord splice slip to give us just shy of a ½ inch of deflection for that particular example. So that was a fairly quick look at the example as laid out and some of the assumptions. I see that a question did come in during the presentation from a user about air gun nails being more common at the job site. Please address hand-driven nails used in the example versus gun nails. The gun nails or pneumatic nails are all covered in evaluation reports. The old legacy report, I believe, was NER 272. If you go to the website for the International Staple and Nail Tool Association, I believe their website is iSanta, I as in India, iSanta.org. You can get copies of the legacy report, NER 272, and whatever the newer national evaluation report is for pneumatic nails. They show the equivalent nail diameters and lengths that are used, and so you would use those nail diameters to either calculate a capacity or use the capacities that they've tabulated in the evaluation reports. And then you would use comparable diameters. So you might need to do some of the math to figure out what the comparable diameters are, then to go back into our tables to grab those G sub A values. I'm not sure if the new evaluation reports actually tabulate the simplified G sub A values for pneumatic nails or not. I haven't looked at the newer reports, but you want to use the equivalent diameter and length approach to do that. There's a second question. So now that you have the deflection calculated, what do you compare that to? Is there an allowable deflection based on diaphragm length? I believe the code spells out what those allowable deflections are for walls. There's nothing specific in the wind and seismic standard that expresses an allowable, but for example, if you have a brick fascia, you're going to have different deflection limits than you would say for some sort of vinyl siding or other type of siding. So you'll have to look at the code limits to determine what those allowables are, because I guess you would have to make the assumption that at that location, the maximum middle of the diaphragm, the diaphragm, if it's deflecting that much, is going to create or bow out, if you will, or push out the shear wall or the wall below it that's running along the long portion of the diaphragm. And so I'm assuming you'd have to compare that to whatever deflection requirements there are in the code for walls in that vertical direction as well. Another question, are there provisions to calculate deflection for a diaphragm that is only partially blocked at the ends only? Or is it proper to base the deflection on the entire diaphragm being unblocked? Only partially blocked. Yeah, we've not looked at a case where you maybe have a partially blocked and unblocked diaphragm. It's either, if you look back at that test data slide that we have, it's either blocked or unblocked. We haven't looked at that partial situation. So again, that's going to require some engineering judgment. I tend to be a little more conservative, so would likely look at the unblocked approach as to determine what my sort of my maximum endpoint would be. Maybe then you could look at if you have this all in a spreadsheet or whatever, and you can run it quickly. You could run the block number just to see what the magnitude of difference is. It's likely going to be somewhere in between, but again, depending on how critical deflection is in the example you're looking at, if you've got some brick fascia or some sort of fascia there that is going to be critical, then I tend to be a little more conservative with my assumptions. Another question, let's see, has to do with slide 18. When the nailing pattern and the horizontal diaphragm varies instead of being uniform, do you recommend using the method shown in the IBC commentary? Nailing pattern varies instead of being uniform. I guess I come back to the same conclusion that I expressed earlier. I think I'd look at what my boundaries are, and as you look at these numbers, you're going to see quickly that the magnitude of difference as you start fine tuning and drilling down to this fine detail doesn't affect your results dramatically. So I'd almost look at it with the tightest nail patterns you've got in one part, the most open nail pattern you've got as another boundary condition, see what the magnitude of difference is, and then determine is it worth the extra fine tuning to try and to take it to that next level of analysis. Question, because deflections are related to variable wind directions, is there a multiplier to use for a long-term consideration due to possible enlargement of nail holes, or is that included in the nail slip deflection counts? Yeah, the diaphragm values that we used already are based on cyclic tests, full reverse cyclic tests, and so that's already accounted for in the background for the values, especially the shear values. So I wouldn't worry about that. That's the cyclic nature of wind on the structures. That's already been accounted for in the design properties. Let's see. Then this is a question about shear walls. Okay, if there are two shear walls, different lengths, and one shear resisting line connected with the same top chord, how are the shear wall deflections calculated? Two shear walls, different lengths, one shear line. I'm going to have to pass on that one. I thought there was a provision in the code. See, I'm assuming that if you're in the same shear line that you've got similar materials. I don't think you're allowed to mix materials in the same shear line, so I'm not sure if maybe you're talking about an offset or something like that. It says it's connected with the same top chord though, so two shear walls of different lengths. I'm sorry, I'm not able to answer that question here off the top of my head, so maybe we can look at that one offline privately, so I'll have a little more time to look into that one. Oh, and there's a follow-up question related. Why aren't shear wall deflections included in the diaphragm deflection calc? Well, if you had an intermediate shear wall somewhere, I mean, this is just looking at, you know, that maximum deflection. We're treating the diaphragm as a long, deep beam. You know, it's a 48-foot long beam, basically, with supports at the ends. So your shear walls are at the ends. Oh, I see. I think I see your question then. So if you've got shear wall deflection at the ends, that would have to be additive with your deflection calculation at the center, because your entire diaphragm is also moving in that same direction. So yeah, that's an excellent point. If your reactions, if you will, at the ends of your deep beam are all moving based on your deflection calcs for your shear walls, then that would also be additive with the deflection at the center of your diaphragm. So yeah, great question, great point. In this specific example, we're just looking at the diaphragm itself, but if your reactions are moving for your beam, then you'd also have to account for that in your limits if you're looking at the center part of the wall where that maximum deflection occurs, again, for your brick fascia or wherever at that location. So great point, great question. Let's see. Okay, the follow-up to the different wall segment question: if shear is assigned to each segment based on length of rigidity. Yeah, I'm just going to have to claim stump the presenter at this point. I'm going to have to go back and research that one a little more for shear walls. I was geared up specifically for diaphragms in this one, and I'm having trouble drawing from my memory on the diaphragm calc. So maybe future seminar we'll look at a diaphragm deflection example, and I can come back to that one. So sorry, I can't get to that one at this point. Here's an answer for one of the questions about deflection limits, IBC 2403.3, framing. Each individual pane of glass perpendicular to the glass pane shall not exceed 1/175 of the glass edge length or 3/4 of an inch. So there's one example of deflection limits for glass panes. I think brick, if I recall, wasn't that L/600 or something like that for deflection limits for brick. Again, my memory's fuzzy on the specific requirements, but you're going to have to look at it based on whatever material you've got that's going to be most critical or most susceptible to deflection. Okay, Dawn, I don't see any more questions here. I'm going to ask if you would to maybe unmute and let me know, did you get any questions to you as the host privately that we need to address?
I sent them to you. I think you've answered all of them. One more came through from Scott, if you look on the box.
Okay, yep,
I'd like to encourage everybody to submit your questions at this point for Buddy if you have any, and he'll take them at this point.
Okay, another
coming through.
Yeah, another answer for the deflection limits, L over 240 for brittle finishes, L over 600 for gravity loads on brick. Huh, that's gravity loads on brick. Interesting. That doesn't account for the lateral loads. Okay, does this equation apply to folded diaphragms as well? I guess we're talking about roof diaphragms in this particular case, and I think the answer to that is yes. This would apply to both a roof diaphragm or a floor diaphragm. Let's see, another answer for the deflection limit for brick, L over 600, but not to exceed 0.3 inches. So it's great to have help for the presenter from all you folks that are aware of the code and going to find those answers. Another question that's come in: if panels are glued, can that be accounted for? I'm not aware at this point of any provisions that account for glue with the assembly. If there's somebody from APA on the call that might have something in the APA literature, please chime in, but I don't believe that we account for adhesives in this. There might be something in the seismic provisions for adhesives, but I wasn't aware that that counted for deflection, but I may be wrong. Okay, large diaphragm, what if adjustments to deflection equations need to be made to obtain inelastic diaphragm deflection? Inelastic diaphragm deflection. If you're talking about going beyond the 1.4 limit, I was not aware that you needed to go beyond that limit of 1.4, since ASCE 7 specifically requires 1.4 times the ASD capacity, and for deflection, then maybe it has to do with LRFD design. I'm thinking that for deflection design, we're just going to use the allowable stress converted times 1.4 for deflection design. So I'm not clear what the question related to inelastic diaphragm deflection. Sorry. Okay, another question. In comparison of calculated deflection to actual deflection, the diaphragm was effectively a diaphragm 6612 in the middle. There's been tests done with nailing in the middle of the diaphragm that's not 6612 to compare basing Gisabe on boundary nail spacing and other edge nail spacing. No, that was, I think we touched on that just briefly in the presentation, where I said we use the nailing for the interior of the diaphragm and not the nailing based on the boundary edge conditions. We just don't have the test data yet to refine the approach that much. So at this point, we base it on the nailing in the middle of the diaphragm. Again, you could try the nail spacing drop that into the equation for the boundary edge nailing requirements to see what the magnitude of difference would be. My suspicion is it's not going to be a whole lot, but that would sort of give you your boundary conditions, if you will, and then you could use that to help in your engineering judgment about whether you refine that further. So, next question: how is deflection calculation affected by roof holes due to skylights, duct penetrations, or roof access penetrations? I believe in the standard, and I'm gonna flip through it here real quickly. There are some limits on the openings that are permitted. At least I know in the wood frame construction manual for 1 and 2 family dwellings, we have a limit on openings in the diaphragm. I'm looking here to see if we have a similar limit on openings. Not finding it here quickly. I'm gonna have to pass on that one as well. I'm not seeing in a quick review a standard where we limit openings in the diaphragm. So I thought maybe we had done that, but no, I'm sorry. I'm gonna have to pass on that one. I'm assuming if they're within, a certain percentage of the diaphragm, you just and they're framed properly per the requirements. It seems to me it'd be similar to shear wall with openings where you're looking at those openings and either looking at maybe force transfer around them, or if they're within a certain percentage of the diaphragm, then you can ignore it and assume it will act as a continuous diaphragm. So let's see. Okay, here's a response to the question about inelastic deflection. The comment here is, I believe that is the amplification factor, C sub D in ASCE 7, section 12.8.6, which is then used for story, drift, and seismic gaps. So thanks for that bit of information there about the inelastic deflection. That looks like it's covered ASCE 7, section 12.8.6. Okay, Dawn, I believe that's the end of the questions I have here. It looks like we're coming up on the top of the hour. Do you want to